let's do an example to give you a flavor. Okay, so evaluate the real integral, the principal value x squared minus 2x plus 2. Okay, that's good. So yeah, this one was what? It was the limit of this guy. Okay, good. All right, so let's look at the complex version of it. All right. So what do I mean by that? Well, uh, what we do is wherever we see x, we put z. Okay, so z squared minus 2z plus 2 dz contour c, and this is the contour. Let me write cr. Okay, so that's the contour, and we split it. So minus rr plus the semicircle part. Okay, fine. Claim the second term goes to 0. Yeah, let me do that first and then we'll do residue. So let me first make this term disappear. Right, okay. So let me take, so yeah. You can in fact expand this, so let me do it here. So this is z minus a, z minus b, where a is 1 minus I, b is 1 plus I. Okay. All right. Now this is a circle, okay? And it's a circle of radius r. So let's do polar coordinates. 0 to pi. We put pi because this is a semicircle. It has angle pi. And we have r ei theta minus a, r ei theta minus b, and I r ei theta d theta. Okay, that's polar coordinates. And then let's do triangle. So okay, and ei theta has norm 1, so you just have r. Okay, good. Now what? Almost there. I have to take a limit in r. Um, right. Now do reverse triangle. Let me write it here. What is a reverse triangle? So reverse triangle is when you have a minus b is bigger than, sorry, um, x minus y is less than the norm of x minus the norm of y. That's reverse triangle. Okay, good. But now this is reciprocal. So it's upper bound. Is that okay? Now you might ask, why do this? I want to do it because I want to get rid of this EI theta. So what happens here is this guy becomes 1. So you have R minus A. And, well, R is positive, so that's fine. And minus B. You see, there is no EI theta. Theta is gone. So this is constant in theta. So you have pi, right? R over R minus A and R minus B. Okay. Now, what was our claim? Our claim is that this integral is 0. Okay. And indeed, this behaves like R over R squared, 1 over R, which goes to 0. So indeed, um, the CR integral of f goes to 0. Okay, good. So that's the first step. Second step, let's just evaluate residue theorem for our guy. So z minus a, z minus b. Let me write them down because now we need them. So 1 minus I, 1 plus I. Okay, now I have to do residue. All right, let's see. So which ones are inside the contour? So you have two poles. You have to answer the question which ones are inside. So let me draw them. 1 plus I, it's over here. 1 and 1. What about this? 1 minus I, it's down here. Okay, so only 1 plus I is inside the contour. Okay, so you only have one residue. So that integral is equal to 2 pi I of residue of where is it, f at 1 plus I. So 2 pi I z minus a, z minus b, times, let me write it here, z minus a, evaluate at z equal to a. And so you get a minus b, which is just, 1 plus I minus 1 minus I. So you get pi. Okay, so now here you can finish. If you're in the final exam, you don't have to tell us anymore. But let me tell you what has happened. Okay, so we have our function, we have our limits. So here you can finish. But let me explain you what happened. Okay, so you have these two guys. We just showed by residue theorem that this is equal to pi. Okay, but it doesn't depend on r. As you can see, there is no capital R. So now take limits in R on both sides. Okay, so you have pi is equal to the limit of R of this guy plus of this guy. And we just showed above that this guy is 0 once you take a limit. And this guy, we define it to be the principal value. And that's it. We found that the principal value of our function is pi. Okay, so let me write down what the function was. Dx. Okay, so that's that.